Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The manuscript, composed by Isaac Newton around 1671, later published as the Method of Fluxions and Infinite Series, presents a unified computational framework for the analysis of continuous change, while its formal publication was delayed until 1736. Its contents circulated among a select group of mathematicians, fundamentally shaping the course of the exact sciences. This treatise, born from the creative intensity of Newton's early years, offers a window into the development of the calculus from a deeply physical and kinematic perspective. The work makes explicit claims about its power to solve problems that had vexed the mathematical world, from finding roots of complex equations to determining tangents, curvatures, and areas under curves. It posits a universe of quantities in a state of perpetual flow, a dynamic world susceptible to a new and powerful form of algebraic reasoning. This essay offers a direct evaluation of the internal claims, procedures, and conceptual structures advanced within that seminal work. Proceeding systematically through its principal arguments, it will examine the methods Newton puts forth, assessing the logic and evidence he provides for their validity and utility, thereby illuminating the profound and occasionally precarious foundations of his analytical. Section 1. The resolution of equations by infinite series. The treatise commences with a detailed exposition on solving equations through the use of infinite series. The core claim here is one of procedural universality for a vast class of algebraic and transcendental equations. Newton presents a powerful algorithm, an iterative recipe for extracting the root of a given equation in the form of an infinitely long polynomial expression. He begins by assuming the form of the solution, typically taking a variable y to be a power series in another variable x. The process involves identifying the first, dominant term of the series by examining the equation's behavior for very small values of its variables, a technique akin to his use of the analytical parallelogram. Once this initial term is secured, he substitutes it back into the original equation and rearranges the resulting expression to create a new equation for the remainder. The same process is then applied repeatedly to find successive terms of the series, with each step refining the approximation of the root. The claim of the method's efficacy is demonstrated through numerous, meticulously worked examples. He applies it to equations like y³ minus 2 times y minus 5 equals 0 to find a numerical root, and to equations like y³ plus r² times y plus a times x times y minus x³ minus 2 times a³ equals 0 to find one variable as an infinite series in terms of another. The internal logic is purely operational. The method's justification is its success in producing results. However, a critical evaluation reveals an underlying set of unstated assumptions. Newton's entire procedure rests upon the presupposition that the solution can indeed be expressed in such a power series form. The text provides no formal proof of convergence or any deliberation on the domain of validity for the resulting series. The argument is one of induction from successful examples. He asserts that the process can be continued as far as one pleases, implying an infinite precision is obtainable. The strength of this section is its demonstration of a robust and widely applicable computational engine. Its conceptual framework accepts the existence and manipulability of infinite sums as axiomatic, a position that embodies the 17th century confidence in the power of new algebraic techniques. Section 2. The foundational principles of the method of fluxions following the treatment of series. Newton introduces the conceptual bedrock of his calculus, the method of fluxions. The central argument of this section is that all mathematical quantities can be conceived as generated by continuous motion. This kinematic foundation is the defining characteristic of his approach. He introduces the term fluent to describe any quantity that is continuously increasing or decreasing, such as a line being traced by a moving point or an area being swept out by a moving line, time is posited as the ultimate, uniform, and independent fluent against which all other flows are measured. The core concept derived from this is the fluxion, which he defines as the velocity or rate of gyration of a fluent. If a fluent is denoted by the letter x, its fluxion is represented by a new symbol, x with a dot above it. This conceptualization makes the calculus a science of motion and its rates. The claim is that any equation relating fluid quantities implies a corresponding equation relating their rates of change. To bridge the gap between static equations of fluents and the dynamic world of fluxions, Newton introduces the moment of a fluent. He describes this as the infinitely little increment or accession to the fluent that accrues in an infinitely small portion of time. This moment is represented as the product of the fluxion and this infinitesimal time interval, which he symbolizes with the letter O. For a fluent x, its moment is the product of its fluxion and the time interval O. The logical status of this moment is the most scrutinized aspect of Newton's entire system. Within his text, it possesses a dual character. It is treated as a non-zero quantity, small enough that its higher powers can be neglected, but substantial enough to be used as a divisor in algebraic manipulations. At the final stage of a calculation, any term still containing the symbol O is discarded, effectively treating it as zero. The section claims that this procedure is a reliable and general way to reason about the rates of change. The evaluation of this claim reveals the source of both the method's power and its subsequent controversy. The kinematic analogy is intuitive and powerful, grounding abstract mathematics in physical reality. However, the introduction of the evanescent moment O creates a logical ambiguity. The work presents this tool without a rigorous axiomatic defense, relying instead on its geometric and physical intuition. The foundation is operational, establishing a set of rules that work, with their ultimate justification residing in the correctness of the results they produce. Section 3 problem by determining the relation of fluxions from a given equation of fluents. This section presents the first great problem of the calculus, what is now known as differentiation. The primary claim is that given any equation relating two or more fluent quantities, his method can unfailingly determine the corresponding equation relating their fluxions. Newton's procedure is algorithmic and direct. He takes a given equation, for example, the equation x cubed minus times x squared plus a times x times y minus y cubed equals 0. He then substitutes each fluent variable with itself plus its moment, so x becomes x plus the product of its fluxion and the time interval O, and y becomes y plus the product of its fluxion and the time interval O. The next step is to expand all the terms in this new equation. This results in the original equation's terms, plus a collection of new terms containing the symbol O. He then subtracts the original equation from this expanded form, which conveniently eliminates a large portion of the expression. All the remaining terms now contain at least one factor of O. He then divides the entire equation by the symbol O. The final, decisive step is to argue that because O is infinitely small, any terms still containing it after the division must be equivalent to nothing and can be discarded. The resulting equation, now free of O, is presented as the true and exact relationship between the fluxions. Evaluating this claim requires close inspection of the algebraic manipulations. The procedure is remarkably effective and yields the correct results. For the example equation, the process yields 3 times x squared times the fluxion of x minus 2 times a times x times the fluxion of x plus a times y times the fluxion of x plus times x times the fluxion of y minus 3 times y squared times the fluxion of y equals 0. The power of the algorithm is its mechanical nature, transforming a complex conceptual problem about rates into a sequence of substitutions and simplifications. The logical fragility, however, lies in the handling of the quantity O. It is used as a divisor, which requires it to be non-zero, and then it is treated as 0 to eliminate the remaining terms. This procedure, treating a single quantity as both something and nothing within the same proof, lacks the rigor that later mathematicians would demand. The claim of the section is therefore one of procedural success. The method works, and its internal coherence is asserted based on the intuitive notion of the moment as a nascent, vanishing increment. Contemporary and later critiques would focus precisely on this point, questioning the logical validity of banishing quantities after they have served their purpose, a process Bishop Berkeley would famously deride. Section 4 problem to determining the relation of fluents from a given equation of fluxions. This section tackles the inverse problem, which is now called integration or antidifferentiation. Newton's central claim here is that his method provides a general route to find the underlying relation of fluent quantities when one is given an equation involving their fluxions. He explicitly frames this as the reverse of problem I, stating that if the solution to one is known, the solution to the other follows. This recognition of differentiation and integration as inverse operations is a cornerstone of the calculus and represents a claim of profound conceptual unification. The evaluation of Newton's method reveals that its generality is built upon a combination of direct antidifferentiation and the powerful tool of infinite series. For simple fluxional equations, where the form matches one of the results from problem I, he could reverse the process directly. He compiled tables of what he called quadratures of curves, which are effectively tables of integrals. If a given fluxional equation could be matched to an entry in his catalogue, the relation of the fluents could be written down immediately. The claim to a more general method, however, rests on the work's first part, when a fluxional equation could be expressed in a form that resisted direct integration. Newton's strategy was to expand the expression into an infinite series. He would then apply the inverse of problem I term by term to this series. Since integrating a simple power term is straightforward, he could thereby produce a new infinite series representing the desired fluent quantity. For example, to find the area under the curve y equals 1 divided by the quantity 1 plus x squared, he would first expand the right-hand side into the infinite series 1 minus x squared plus x to the 4th power minus x to the 6th power, and so on. He would then integrate this series term by term to find the area as the series x minus 1/3 of x cubed plus 1/5 of x to the 5th power, and so on. The synthesis of his two major techniques, series manipulation and the fluxional method, is the foundation for his claim of generality. The argument's strength is its immense practical scope. It provided a way to find quadratures for curves whose integrals were previously inaccessible. The implicit assumption, once again, is the validity of these infinite series operations. The term-by-term integration of an infinite series is performed without a formal proof of its legitimacy, but the results it generated were consistently correct and powerful, providing strong inductive evidence for the method's claims. Section 5 applications, tangents, curvature, maxima, and minima, the final part of the treatise, is dedicated to demonstrating the utility of the fluxional method by applying it to a suite of challenging geometrical problems. The overarching claim is that the abstract machinery of fluxions and fluents provides a universal key to solving these diverse problems through a single, unified procedure. For the problem of drawing a tangent to a curve, Newton argues that the subtangent, a key geometrical length, is given by the ratio of the fluent y to the quantity formed by the fluxion of y divided by the fluxion of x. This translates a geometric construction into a simple algebraic calculation using the result of problem I. He provides examples for various curves, showing how this rule works consistently. For the problems of finding the maximum and minimum values of a quantity, he makes the crucial claim that at such a point, the fluxion of that quantity must be equal to 0 or infinity. This insight transforms the search for extrema into the algebraic problem of solving the equation where the relevant fluxion is set to 0. This was a powerful simplification of the methods proposed by Fermat. Perhaps the most impressive application is his treatment of curvature. He claims that his method can determine the degree of crookedness of a curve at any point. He derives a general and quite complex formula for the radius of curvature involving the first and second fluxions of the curve's coordinates. This was a significant advance, providing a precise, quantitative measure for a concept that had been understood only qualitatively. An evaluation of these claims shows them to be entirely substantiated by the results. This section serves as the ultimate justification for the entire system. While the logical foundations regarding infinitesimals might be open to philosophical debate, the method's ability to solve these notoriously difficult problems with elegance and efficiency was undeniable. The claims are of operational power and unifying perspective. The same fundamental procedure, finding the relation of fluxions from fluents, is shown to be the single tool needed for tangents, extrema, and curvature. This demonstration of practical mastery is the work's most persuasive argument. It asserts that whatever the philosophical status of its foundations, the method of fluxions is validated by its fruits, providing correct and novel answers to the most pressing questions in geometry and analysis. In conclusion, Isaac Newton's The Method of Fluxions and Infinite Series constitutes a monumental claim for the power of a new, unified system of mathematical analysis. Its internal arguments, evaluated section by section, reveal a work of profound computational genius, characterized by algorithmic elegance and immense practical utility. The claim to solve equations via infinite series is supported by a robust iterative procedure, whose reach is limited only by unstated assumptions about the analytical nature of functions. The work's core argument for a calculus based on kinematic principles of fluents in motion and their fluxional rates provides an intuitive and physically grounded framework. The central procedures for what we call differentiation and integration, problems I and who, are presented as infallible algorithms, with their claim to generality resting on a brilliant synthesis of direct antidifferentiation and the versatile tool of infinite series. The logical coherence of the system, particularly its reliance on the ambiguous nature of the infinitesimal moment O, would foster generations of mathematical inquiry aimed at securing its foundations. Yet, the work's final and most compelling claim, demonstrated through its application to the classical problems of geometry, is one of operational supremacy. The treatise shows how a single, coherent method can dispatch a wide array of complex questions with mechanical precision. Its enduring significance rests on this very point. It presented a vision of mathematics as a powerful engine for calculation and discovery, a vision whose practical success propelled the scientific revolution forward, even as its foundational subtleties provided the impetus for the future development of mathematical rigor. The work asserts its own validity through the sheer force of its results.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.